started. Welcome back, everyone, to the fourth day of this boot camp. It looks like even the weather is back to normal today. So we have Jonathan telling us more about probabilistic and combinatorial methods in coding theory.
Thank you. Okay. Yeah, so we left with a cliffhanger yesterday, so let's recall where we were. Okay, so we saw the definition of a code that we say is locally similar to a random linear code. So what does it mean to be locally similar to a random linear code of rate R? So we have this random code ensemble. Okay, so we should think of C as a random code taken by some other distribution, not a random linear code, usually a more structured distribution. And then we can ask for a given tuple of code words, what's the probability that C contains all of them? And we say that C is locally similar to a random linear code if for any tuple this probability is bounded from, okay, so yesterday we said similar, but actually bounded from above is enough for what we're trying to do, and this is going to somewhat matter today. So it's going to be bounded from above by the probability that the same tuple belongs to random linear code, okay, which is just this exponential thing, this negative exponential thing in the dimension of the tuple. Okay, and the theorem that we saw, and this comes from the threshold characterization for local properties of random linear codes, we saw that if we have some random linear code ensemble that's locally similar to a random linear code of rate R, then it achieves all the monotone, local, and symmetric properties that we expect to achieve by a random linear code. Okay, so any monotone, local, and symmetric property that a random linear code achieves, this random ensemble would also achieve. Now, another thing I added that we didn't have yesterday is that we actually, like, the locality here is actually going to be a parameter. Okay, so I'm talking about like k, being k locally similar to random linear code means that this holds for tuples of up to k vectors. Okay, and then what we're going to get, the larger k is the more similar, like the more similar we are to a random linear code. And then here we're going to get more properties because we're going to get up to this locality. So for example, you can think of the locality as the list size for list decoding. Okay. Okay. Nice. And I want to warm up by showing you a certain ensemble which is very well known, or well, it's a variant of a very well-known ensemble for which it's pretty easy to prove this local similarity to random linear code. So I'm talking about the Wozencraft ensemble. So this is used in the construction of, well, I think it's the first known construction to, like, the explicit construction of good codes, Eustace codes. So this is a part of that construction. So, okay, so what's the, I'm going to talk about the generalized Wozencraft ensemble, but first let's just recall what is the Wozencraft ensemble itself. So we think about, this is going to be a code of rate 1/2, and we're going to think about words of length n, which are divided into two parts, each of size m. Okay? And the way these words work is as follows. So we're going to encode elements of the field of size 2 to the m naturally into just sequences of m bits. Okay? And what's a code word? So we need to sample some random alpha from the field fq, okay, where q is, sorry, I didn't write that. Q is 2 to the m, okay? So I'm sampling some alpha from the big field, from the field f2 to the m. And then the code words are going to be all the words of the form, it's going to be pairs of x, and then this alpha times x, okay? And I'm going to encode them into m bits and m bits. So the randomness comes from the sampling of alpha. And you can already see that this is less random than a random linear code, because for a random linear code, I need roughly n squared random bits. Here, I only need around n random bits to sample an element from this field. Okay, so it's less random. And I get this code of rate 1/2. Okay, and this code is one locally similar to a random linear code of similar rate, of rate 1/2. Why? Okay, so to prove one local similarity, I just need to show you that if I take a tuple of one vector, or just a vector, then the probability that it's contained in the Wozencraft code is roughly the same as it would be in a random linear code, which should be like 2 to the minus n over 2. Okay? And this is really the case. Why? Because take some y, take some string y, and ask what's the probability. We want to ask what's the probability that this is contained in the Wozencraft ensemble. What y can be, like, we think of y as an encoding of two elements of the field. So there's only one way to write y as encoding of x, and then, well, the second field element would need to be like some beta times x. Okay. And then the only way for this word y to be contained in the Wozencraft ensemble is if alpha equals beta, which happens with probability exactly 2 to the minus m, which is exactly 2 to the minus n over 2. Okay. So this is one locally similar to a random linear code, which is a very strange way to state a fact that you probably already known if you took a coding class that mentions this. Okay. So now the corollary, for which we really don't need this whole sophisticated machinery of the threshold theorem of random linear code, but we can use it if we want. So the corollary would be that the Wozencraft ensemble achieves the same one local properties as a random linear code of rate 1/2. For example, what's a one local property? So the minimal weight is a one local property, right? You just need to show that a code has weight less than something. I only need to show you one. For linear code, I only need to show you one bad witness, which is a short word. Okay, so in particular, it achieves the random linear code achieves the GV bound for distance. So this also achieves the GV bound for distance. Okay, how do we generalize this? So we do the same thing, but instead of picking a random alpha, we're going to pick a random polynomial over the field of degree at most k. And then our code words, instead of taking x and alpha x, I'm going to take x and this polynomial applied to x. Okay. And I'm not going to prove this claim, but you can easily prove it using exactly the same sort of logic. Okay? We just need the fact that a polynomial of degree at most k is defined explicitly, is uniquely defined by any k values, right? And that's exactly going to mean that any k tuple is going to belong to this code with probability at most, well, exactly what we expect in a random linear code. Okay. So these codes are k locally similar to a random linear code of rate 1/2, and in particular, they achieve, for example, the list decoding GV bound that's achieved by random linear codes. So this is already a nice and simple de-randomization result that we get from the. This is actually, I think this is not. I think this doesn't appear in any paper, but it's like this nice toy example. And it already gives us codes that achieve the list decoding GV bound with n randomness instead of n squared randomness. Okay, so now let's go to a more deeper result. Okay, so I'm going to explain what's like. There are a few notions here that need to be explained, but the theorem says as follows: let D be a low bias code. Low bias just means, so you can just think of it. I'm only going to define it, say, in the case of the binary case. So low bias just means that you have good distance, but you also have good distance from the not just from the all zeros. Okay, you're not just far from the all zeros word, but you're also far from the all ones word. Okay, so in other words, all the weights of the code words, other than the zero code word, lie very close to 1/2. Okay? And these are, in particular, you should think of D as having very low rates, so that it can have this property of like having very low bias. Okay, so these some low rate code which has low bias, and then what we do is we randomly punctuate, which I'm going to define exactly. But just think of like taking C to be the coordinates of C are going to be randomly sampled from those of D. Then we're saying, so this is work with Venkat, we're saying that C is going to be locally similar, and I'm not going to go into the exact dependence of K on the parameters here, but C is going to be locally similar to a random linear code. Okay. And one caveat for this theorem, I'm going to talk about like what this can be used for. But one caveat is this we're going to see why this can requires us to have constant alphabet size. So for example, this cannot be used to argue about what we wanted the most, which is Reed-Solomon codes. Because randomly punctured, like if you take, this is going to be something that will be discussed at length at the later part of this lecture, but if you take the Reed-Solomon code with the full evaluation set that's evaluated on the whole field, and you randomly puncture it, you get a Reed-Solomon code evaluated on some random set. And one motivation for studying this was exactly so that we can study these sorts of Reed-Solomon codes over random sets. And then show that they are locally similar to random linear codes. So for example, show for list decodability. The problem is really that this is not going to work explicitly using this theorem, because this theorem needs the alphabet size to be small, where Reed-Solomon codes needs the alphabets to be at least n. Okay, so before explaining and going deeper into this theorem, I'll just mention that this random puncturing was recently somewhat de-randomized by Potterman and Pine in a paper that will be presented in ITCS here on Wednesday, I think, right? Okay, so let's define puncturing more precisely. So puncturing is the operation by which we take a code. So again, we think of D as some low rate and rather long code of length m, and we create from it a new code which is much shorter, okay, of length, code C of length n, where n is going to be smaller than m. Right, so we just pick, okay, if these are the code words of D, then just the code words of C are going to be the code words of D minus, or like we just choose certain coordinates and throw off the rest. You should think of most of these columns as being red and only a few being blue. Okay, so we keep only a small portion of the coordinates. Okay, and if we create C at random by picking the coordinates at random from here, then we say that C is a random puncturing of the code D. Now, one motivation or one intuition for what we're doing here is the observation that a random linear code itself can be seen as a random puncturing. So if we take D to be the Adamar code, which is exponentially long in n, okay, so it's this very, very, very long code, and we randomly puncture it, then what we get is exactly a random linear code. The thing is that this is a rather random process because the Adamar code is such a long code, so we need a lot of bits to sample from it. Now, if you could start from a shorter code here, then you'd get something with more structure, because presumably some structure from the top code from D goes over to C. For example, if D is a Reed-Solomon code, then C would also be a Reed-Solomon code of a random set, which still has a lot of algebraic structure. There's a case where our theorem is actually applicable. So if we take D to be a dual BCH code, and these are codes with constant alphabets that do have low bias, then we get, again, some of the algebraic structure of the dual BCH code in C as well. So this gives us, so this theorem would apply to certain more structured analogs of random linear codes. Yeah, so I'm stating here, for example, that a Reed-Solomon code can be seen, a Reed-Solomon code of a random evaluation set can be seen as such a puncture. Okay. Okay, sorry. What our theorem is going to say is that as long as this code has low bias, then this code is less decodable and all the nice stuff we can get from random linear code. This code is going to be similar to random linear code. Okay. So let's, for now on, we're going to focus, for this theorem, we're going to focus just on the binary case. But this is going to work similarly for any constant size. Yeah, so the theorem says the following. Suppose that every word in U has normalized weight close to half. So again, for the Adamar code, it's going to be exactly half. And this is, you can't get weight exactly half with a code less, not as long, like which is shorter than the Adamar code, but you can get close. You can get with much shorter codes. For example, Tashma codes, which only require length linear rather than exponential in n, can get you very close to perfectly, like so Adamar code has 0 bias, but the Tashma code would have like very small epsilon bias with a much shorter code. Or say take a dual BCH code. And then the theorem is that if we do this operation in such a code D, then C is going to be locally similar to random linear code, and then C is less decodable and less recoverable as a random linear code. Okay, and I want to quickly give you an idea of how this is proven. Okay, so we're going to do a comparison between a random linear code and our code C, which is a puncturing of D. Okay, so we have, these are going to be all the code words of D. And yeah, we have a puncturing of them, and then we get this new code C. And then this is going to be the Adamar code. And if we randomly punctuate, then we get a random linear code. Okay? So we can really think of, okay, so this operation is happening side by side. Here we puncture D, we get C. Here we puncture Adamar code, we get a random linear code. Okay? And now we need to show that a tuple of code words appears here and here with roughly the same probability. So let's fix a tuple, the same tuple in both cases. Okay? So here I fixed L+1 code words, and here I'm fixing the same L+1 code words. And I want to know what's the probability that these code words appear here versus what's the probability that they appear here. Now, how would I do that? I can take okay, we're going to say the following. The probability of getting like this tuple of code words. So this tuple of code words can be born, this is L+1 code words, they can be born from any L+1 code words here. Right? So we're going to sum over all the L+1 tuples of code words here. And for each one, this is justified. Again, this is just a proof sketch, but for each tuple here, we just want to compute the probability that this tuple is going to yield this tuple here. Okay. So what does this depend on? Okay, now I have a specific tuple of L+1 code words here, and I want to know what the probability that it gives us this. Okay. So this depends only. So the arrows here can be a bit confusing, like because I put them, they don't intersect, but they don't cross. But you should think of the arrows as they can also cross with the same probability. Okay, you should just think of every column here as being chosen uniformly and independently at random from the columns here. So the probability of getting a certain tuple of code words here depends solely on one thing. It only depends on the column distribution of this. And similarly here, okay, the probability of getting this tuple here depends solely on the column distribution of this. Okay, so we end up with the following thing. We have L+1 code words here and L+1 code words here. And we want to show that some probability that depends on the column distribution of these columns happens. So this probability that depends on this column distribution happens with similar probability to this something here that depends only on this column distribution. Thus, what we really want to show is that for these code words, the distribution of these columns is similar to the distribution of these columns. So this is what this all reduces to. Just like looking at tuples of code words in the mother codes, okay, in the Adamar code versus some other code, and comparing the column distribution, the empirical column distributions of the columns that we have here. Okay. Now, for the Adamar code, the column distribution is uniform. That's one way to characterize the Adamar code. That if you take linearly independent code words, then the column distribution is exactly uniform. So really what we want is to show that here, the column distribution is close to uniform. Okay. And this is what's left here is just doing this via Fourier analysis. So if you, okay, so I'm not going to actually go into the Fourier analysis. I'm going to say a few hints for whoever is fluent in these sort of arguments. That if you look at this distribution and think of it as some function, then okay, the distribution itself. So it's a function over f2 to the L plus 1. Yes.
B should be L plus 1 on the bottom right there, right? The column distribution of H is uniform.
Oh, I wrote B. Yeah, it should be L plus 1. Yeah, thanks. Can you remember? Can you tell me that later? I'll fix it for the yeah. So okay. So just think of a function of this distribution as a function. Then its Fourier coefficients are determined exactly by the weights of linear combinations of these words. Now, the linear combinations are themselves words in the code, so they're all of low bias. So all the Fourier coefficients are close to 0. Okay? So here, all the non-trivial Fourier coefficients are 0, and here they're all close to 0. And so the distributions are close in their Fourier in their Fourier coefficients. So they're also close. So we're also close in the prime base. Now, if you followed this argument, then you can also see why we need constant alphabet size. Because this transition from similarity in the Fourier basis to similarity in the primal basis involves a hit of the size of the domain. So in the binary case, the size of the domain would be like 2 to the L plus 1, which is a constant because we think of L as being a constant in these words. But if the alphabet size is Q, then that would be a hit of Q to the L plus 1. And where Q starts being large, like for you think of Q as being as being N, then this is something that's completely unmanageable. Okay. Great. Okay. So that was this theorem, and this is so for example, it gives us that again that we can, it gives us certain randomizations for random linear codes. It says that puncturing many other more structured codes gives us some nice structured randomly punctured codes also have some structure, and they are locally similar to random linear codes. So they have all the list decoding properties, which is very nice. So this exemplifies the basic method. But I promised that I'm going to talk to you about Reed-Solomon codes at some point. So we're getting there. In order to do that, I first want to have a discussion about all the drawbacks of the method I described in the last hour and a half of my talks, yesterday and today. So just like to say what method I'm talking about the method where we use the threshold theorem, random linear codes, to show that another code ensemble is similar to that another code ensemble has this local similarity property, okay, to random linear code, and thus say something about its list decodability and its recoverability. So what are the drawbacks of this method? There are quite a few. I listed them. Okay. So first, locality is necessary. So maybe I should say I should apologize. So I have a friend who came to me yesterday and told me that when I spoke about this yesterday, I presented the problem, I presented list decodability as if I said, yeah, well, L is obviously a constant, and list recoverability, which is, I guess, even a worse it's a worse mistake on my part. I presented the list recoverability scenario as if L is always a constant. And this is not true. There are many, many interesting and important questions, especially to the pseudo-randomness community, which I have deeply hurt, that involve L being large. Yeah, I was okay. There really are very important questions. Yeah, I mean, I'm even thinking about some of them. So yeah, I should have said that. So, for example, here's a question that this method cannot address. So just consider a random linear code, and think about list recoverability, where we have combinatorial rectangles. Okay, so this is like going to be some big field, FQ, and think of combinatorial rectangles where in each coordinate we get Q over 2 letters. Okay. So then a random rectangle has roughly Q to the Rn is the size of the code, and 2 to the minus n is the probability that a random word appears in the rectangle. So in a random rectangle, we expect Q to the Rn times 2 to the minus n code words. And if Q is large enough and R is not very small, then this is an exponentially large number, okay? Because Q to the Rn is going to win over 2 to the minus n. So this is an exponentially large number. And then the question is, what's the probability? Like, can we show that with high probability, the rectangle, the combinatorial rectangle that has the most code words does not deviate from the expectation by more than an epsilon fraction, okay? So this is a pretty natural problem that we don't know how to solve. And the reason that this method is useless against it is because the locality here is, this is not local, right? Like to show you, at least naively, to show you that a rectangle the code does not satisfy this property, I need to show you this number of code words, okay? So this is not a local witness. Cool. So this is an open problem. Like this is also the drawback session is also like an open problem session. Okay, it's a combination of the two. Next. Okay, so this method can only deal with what I term sigma 1 properties. You can think of this as NP or maybe co-NP properties. What do I mean by that? So to show you that a code is not list decodable with constant L, I just need to show you a short witness. Okay. So this would be like co-NP, right? Like list decodability is like co-NP. In order to, I can easily convince you with a small witness that the code does not have this property. Okay. And these are properties that in logic are called sigma 1 or pi 1. These are properties that are you only need one quantifier to define the property. Okay. So it's like not being list decodable is equivalent to there exists a witness such that something which is easily verified. But of course, sometimes we want to talk about properties that are not of this form. So one, I think, like the most well-known example is if so thinking about stochastic channels usually leads to properties that have more than one quantifier. Here, I'm going to give a different example, which is kind of like a toy. It's not a toy problem because I don't know how to solve it, but it is a problem that I came up with in thinking about what would generalize the notion of sigma 1 properties for this viewpoint that we have on, say, random linear codes. So say that a code C is row L covering the covering is, okay, so these are covering codes. Okay, generally, a row covering code is a code in which covers the space with balls of radius row. Okay, so you put a ball of radius row around each code word, and and you say that the code is row covering if this covers the entire space, the entirety of F2 to the n. And note that here it's easier to be, usually we're used to we're used to lower rate giving us better combinatorial properties. Here it's the opposite. Here it's easier to be covering if your rate is higher, right? Because you have more code words to cover with. So we said that the code is row L covering. And this is, if I remember correctly, I didn't, I don't think I defined it. I think this is something that has been studied. I think it even interests some people in certain more applied fields. So we said that the code is row L covering if every x in f2 to the n is row close to at least L code word. So in other words, every word in the domain needs to be covered not by 1, but by L balls. Okay. And then the question is, what's the rate threshold here? For what rates can we expect the row L covering property to hold for a random linear code? The thing is that this is not a sigma 1 property. Okay, I don't know witnesses for easily verifiable witnesses here. Why? Because to state this property, right? What does it mean to be row L covering? It means that for all elements in f2 to the n, there exist L code words that cover them. Okay, so we switch quantifiers. When we switch quantifiers, it becomes the way I just described it. It's what's called the pi2 property. It's sigma 2 or pi 2 are when we have both quantifiers. Pi is when we start from for all, and sigma is when we start from from exists. Okay, so it is interesting if we can somehow generalize this method to more complicated properties in terms of in these logical terms. This is somehow analogous to thinking about for example, the polynomial hierarchy in complexity. Okay. Another drawback is that being locally similar.
This question, is the answer known just for random codes? Like in formula?
My guess is that yes, but I didn't I didn't think about it. This is a question I thought about very little. I give it mostly as a sort of illustration for what sort of for a natural property that's pi2. But I really haven't seriously thought about this question. I also haven't seriously researched what's known, except that I am pretty convinced that the answer to this specific question is right now not known. But I don't know if it's because no one seriously tried to solve it, or is it really difficult? My guess is that it is somewhat difficult.
When L is 1, this is the covering radius. So
yes.
One way the answer to this might be known is that once you get one code word, maybe you actually get lots of code words.
Yeah, that's
no sort of gradation.
So I think I saw somewhere. Well, okay, I'm speculating because I think I read somewhere that this is not the way it works, but I'm not sure right now. Yeah.
It's not. It's definitely interesting.
Yes. Okay. Okay. Next thing is that we think of So we thought of these examples that I showed. For example, these randomly punctured codes and the generalized Wozencraft ensemble. I said that they somewhat de-randomize. They somewhat de-randomize random linear codes. So we say that any code which has this local similarity property, okay, again, that tuples appear in C with the same probability that they would appear in a random linear code. So these tuples, so these codes are local, are what we call locally similar to random linear code. The problem is that these codes must be random themselves. Like we're not gonna get a deterministic code to satisfy this. And moreover, you can't satisfy this property with less than order of n random bits. Why? Because to get something to appear in the code with probability 2 to the minus 1 minus Rn, so there needs to be an event that happens with probability 2 to the minus 1 minus Rn. And this is this resolution. Like this is too fine-grained to happen if you don't have n random bits, right? Like just like the log of this is order of n, well, minus the log of this is order of n. So you can't get this sort of probability with less of an order of n random bits.
And K, right?
Sorry?
And K.
Yeah, I'm thinking. Okay, sorry. Yeah, I again assumed that the locality is a constant. Yeah, so this would be like order of n times the locality for what you really want. So this completely. This means that we're not going to de-randomize using just this method below this order of n threshold. And this open problem actually is, it's a much more general open problem than just concerning the question I showed about random linear codes. But generally, this has to do, I believe, with the fact that we know how to achieve, just like to construct codes that achieve the Gilbert-Varshamov bound with order of n random bits, but we don't know how to go below that. I'm being slightly careful here. Maybe we know how to get like order of n over some log n bits or something like that. I'm not sure, but essentially we don't know how to go along the order of n random bit threshold for the Gilbert-Varshamov bound, and it's kind of for similar reasons. The way we know to prove that something satisfies the Gilbert-Varshamov bound, the original Gilbert-Varshamov bound, okay, the one for distance. The way we know how to prove this bound is only by showing that the probability of a given code word is this. Okay, and whenever we try to go this way, we're not going to get better than order of n random bits. Okay, and the last drawback of this method, and this is what we're going to talk about for the rest of these talks, is that in the method I showed, the alphabet cannot be large. Right, so I talked about this a bit yesterday, but I'll try to recap quickly. So I recall that in this method, we do a union bound over all the possible row distributions for a matrix in F2 to the L plus 1, but whatever. Right, and we said that, okay, how many row distributions are there? Very roughly n to the 2 to the L. This is an upper estimation, but it's not very... It's this question? No, it looks like, oh, you're doing this. I thought you're...
My thoughtful face.
Okay. But, yeah, this, I don't know. Trying to figure out what this means. Okay. Yeah, okay, so we need to union bound over n to the 2 to the L distributions, which is fine because this is a tiny number. This is a polynomial in n. But for general Q, this number is going to be n to the Q to the L. And really, I'm right. And then, like, if, for example, you take Q to be n, which is like Q needs to be at least n for Reed-Solomon codes, then you get like n to the L types. So this is something horribly exponential in n, and then union bounding over this is going to kill you. There's maybe another intuition I can give here is that, so in this case, right, like you have, what is this distribution? You drop n balls into 2 to the L bins. And n is, if L is constant, then n is much larger than 2 to the L. So, every bin is going to have some fraction of the balls. And this is stuff that we know how to work with. Here, you have Q to the L bins. So, for example, think of n to the L bins, and just n balls. So, you're probably just going to have, most of the bins are going to end up empty, and some of them are going to have one ball. So, remembering the distribution is just like, it doesn't really lose information. Like, like it tells you exactly, when you remember exactly what are the full bins and what are the empty bins, and it pretty much tells you, up to this reordering of the matrix, which is not the big part of the number of matrices here. It doesn't really forget enough. Okay, and the whole idea of remembering just the distributions is that you forget enough information that you can do a union bound. Okay, so this really doesn't work here. So you need another framework for this. And then really the question is there any hope of reasoning about, for example, Reed-Solomon codes with Q, where Q needs to be at least m, with this method? And the answer is that not with this method, but with some analogous and properly suited method. Okay, so just to recap, what's the Reed-Solomon codes? Because from now on we're going to be talking about them all the time. So you pick some alphabet Q, and you feel like your alphabet size is Q, so you think of the field FQ. You pick a rank K, and you choose some subset S of FQ to be your evaluation set. And then your code words are just evaluations of polynomials. Each code word is a polynomial of degree less than K over the field, and the code words are the evaluations of this polynomial over S. We denote this code by RS Reed-Solomon with evaluation set S and degree K. And right, so this code has dimension K, and its length is just N, which is the size of S, so the rate is K over N. And we note that since S is a subset of FQ, and N is the size of S, then it must hold that N is at most. Okay, so these are Reed-Solomon codes. Maybe I should state one more thing. So for Reed-Solomon codes, we have the obvious, like one obvious choice of S is just to take the entirety of FQ. And that's called sometimes the full Reed-Solomon code, where we evaluate over everything. And what we're mostly going to concentrate on is the case where S is chosen is a smaller set of size N, which is sampled at random for FQ. And these are we're going to call these random Reed-Solomon codes. Okay, random Reed-Solomon codes is short for Reed-Solomon codes where the evaluation set is random. Okay. And then we want to know, do there exist Reed-Solomon codes that achieve the list decoding bound, the list decoding GV bound? And also, if they exist, how large does Q need to be? We generally want the field size to be as small as possible relative to the length. Okay. So this question was quite extensively researched, including by some of the people in this room. And all, okay, so there's one notable work about the full Reed-Solomon code that I didn't mention here. The reason I didn't mention it here is that it's a negative result. Okay, it shows that in some parameter regime, the full Reed-Solomon code does not achieve list decoding capacity. And these are all positive results about the random Reed-Solomon code. Okay, so these, I mean, this one, I think, Reber-Wooters, I think, is 2014 or something like that, ish. I never know, like, whether to think about the year it was uploaded to archive or the year it was published. Or yeah, it's hard to follow sometimes. And then all of these, I think, are like starting from 2020 all the way to less than a year ago. So this is all really recent stuff. And there's really a buildup. Like if you follow these works, you can really see a buildup of many notions that are useful, that turn out to be useful, and then increasingly more sophisticated techniques to work with them. And most recently, there have been positive answers to the question I gave before. Okay, so it shows that random Reed-Solomon codes achieve the list decoding GV bound. And these, okay, so this was shown by Barkensiak, Gopi, and Makam, but this is for exponentially large field. Then Gu and Zhang. Am I okay? Okay. I know the feeling of like just like being used to people butchering your name and just like, oh yeah, it's fine. Sorry for that. So yeah, so they took the field size down to quadratic in N, and then we have Omar Venkat and Ray Lee, which took this down to linear. And And also say that list recovery is also being researched, but with his code, and it's also very interesting. We just know less about it. So this is just to recap about like the recent interesting results. Now, I'm going to focus on this result, which is the state of the art. Yeah, I'm going to do, okay, so I'm going to do something. So here's the thing. I have, with two students, Matan Levy and Nikhil Shagmitaya, we have a certain work which in particular recovers this result by some other method, and also relies on notions from this work. So it's not, and I kind of debated on what exactly to show, because okay, so I really think that this work, this AGL, really relies on a certain types framework, even though I don't know if you guys see it like that, but when I read it, I certainly think of it as having some types framework. And our work has this types framework put very, very explicitly. And I'm going to present a sort of mishmash of my view of this and the AGL view of this, and we're going to be talking about essentially how to show that random Reed-Solomon codes achieve the list decoding GV bound. I also mentioned that until this work, we didn't know that random linear codes for large Q achieve the least decoding GV bound. So this work, this AGL, also shows that. And kind of interestingly, there's somewhat a partial reduction in AGL from, like, in the opposite direction to what I showed you so far. Right? Like, yeah, the way to show that random linear codes achieve the least decoding GV bound relies on a theorem about Reed-Solomon codes. So it's the opposite of what I showed you so far. In our work, that's not the case. So we independently show in a more elementary way that random linear codes achieve the least decoding GV bound, and then we show a reduction from that to Reed-Solomon code. So in our work, it's really a reduction from random linear code to Reed-Solomon codes, which is the more, this is the direction I've been trying to sell you so far, in these talks. Okay, so we'll start getting into the details, and then I'll try to give some sort of map to what's going on. Okay. So the first thing is that, as I explained before, when Q is large, the types framework that I showed is just inadequate. Okay? Because the row distribution of A, like remembering, okay, so think as, let's recall what the types framework does. So we have A, which is a witness matrix. Okay, this matrix is a witness to it's what we call a row clustered matrix. Okay, it's a witness to the fact that a code containing these columns is not list decodable. And in the types framework, we want to do union bounds over such matrices. We want to show that such a matrix is unlikely in our code. So we want to do a union bound over them. And in order to do union bound, we need to divide them into classes. Sometimes we call these classes types. Okay, so we divide the bad matrices, the witness matrices, into types. And as I showed, remembering the row distribution of this matrix A now contains too much information. There's too many types. It's too fine-grained. We need to forget more. On the other hand, we still need to retain the relevant information so that we can bound the probability that a code actually contains a matrix of the given type. Okay, that's the trade-off. You need types that remember the least amount of information that still allows you to give some meaningful bound on the probability of a code containing such a matrix. Okay, and the main The main idea that we need here is that for a given row in this matrix, I'm not really going to care what's the letter here, and what's the letter here, and what's the letter here, and what's the letter here. I'm only going to care for each given row here about the relationship between the letters in the given row. So I'm only going to care about identities. Okay? So formally, with each row of this matrix, this stat matrix, we associate a partition. We partition the coordinates of the row into sets. Okay? And how do we partition them? According to the identity. These are just going to be the classes of the identity relation. Okay. So with this, if this row is a vector z, then we think we just remember that z is going to tell us that the ith coordinate and the jth coordinate of z are identical. And then for a given matrix, here's the information. Now I'm going to tell you what are going to be our types. What are our classes for? Are we until 10:30 or yeah? Okay.
Sorry, 10 minutes.
Yeah. Okay. I can. Yeah.
You're going to continue, so you can stop.
Yeah, I can. I'll just finish 10:30, and hopefully it's going to be like a reasonable place to halt. Okay. So for a given matrix A, we're going to remember the following. We're going to remember the partition associated with each row A. And there's also one other thing that I'm going to need to remember. That's going to be the row span of A. So what do I mean by the row span of A? The row span of A is just a way to think about what are the linear relations between the columns of A, right? Just like note that, right? For example, if if I have a matrix where I have 3 columns, x1, x2, and x3. And suppose that I have a linear relation between them. For example, x3 equals, or 2x3 equals x1 plus x2. Okay, so suppose I have such a relation, then this is going to be evident in the right. So this relation will hold for every row of this matrix. So this linear relation will be evident in the row span, because if all the rows are going to have this relation, then the row span is also going to have this relation. Okay, so I'm going to see. So the row span is not going to be like in a generic matrix. The row span will be, because these matrices are tall and thin. In a generic matrix, the row span would just be the whole of fq to the L plus 1, but there are also cases where I have such relations, and then the row span is going to be smaller. So this is a way to retain that information, and that's going to be important. But but this is really a very small amount of information, because this is independent of n, right? The row span is just a subspace of fq to the L plus 1. So the amount of information here does not depend on n. This does depend on n. This is really, I remember, a partition for each row. Okay. And importantly, the information I retained is okay. So these are okay. So think of the classes I just defined, right? So what do I mean by type class? Can say that. Sorry. Yeah. So what do I mean by type class? I mean, consider 2 matrices that have the same type. So they have the same list of partitions and also the same row span. Okay. So what I'm saying is that 2 matrices that have even just the same list of partitions are also either both are going to be witnesses for not being list decodable, or both are not going to be. Okay, because when I think of the geometry of the L plus 1 columns of this matrix, I really only care about identities. I don't care about the changing the values as long as I retain the same identity profile. Okay? So any geometric property, for example, list decoding and list recoverability, is going to be unaffected by these sort of changes. And that means that that if a matrix is a witness for non-list decodability, then all of its type class is going to be that. Okay, so in other words, the bad witnesses for list decodability can be presented as a union of these classes, which is with what we wanted. It's also what we got in the previous framework. Okay, and the same goes for list recoverability and all of our natural variations. And in general, let's give a name, local identity property. Okay, so it's a property which is local and concerned with identities. And any such property can be expressed as a union of these type classes. And almost everything I'm going to say for the rest of this talk, is going to be correct for any local identity property. Okay, so just how many types are there, right? The problem we started from was that there were too many types if we wanted to remember the exact distributions. I'm saying that by going from remembering distributions to just remembering these identity partitions, the number of types has dramatically decreased to a manageable level. Okay, so at most, L to the L equivalence relations, specifically the Bell numbers, which give us this the exact quantity, but this is this is an easy upper bound. So how many types are there? Okay, so you need to remember. So this is just Q to the L squared is just an upper bound on the number of on the number of subspaces of FQ to the L. Okay, so this is going to be the number of rows there, and then this is going to be the main part. Okay, so this is the sequence of partitions. So there is L to the L, or L plus 1 to the L plus 1, but we remember n of these, so there's an n as well. Okay, and this number is tiny. Okay? Why is this a tiny number? Because taking Q large enough, for example, take Q to be at least L to the L over epsilon, okay? Then if we try to measure this number on an epsilon basis, then this number is less than Q to the epsilon n. And Q to the epsilon n is tiny because it means that if we change the rate of our code by an epsilon fraction, then we manage to overcome this for our union bound. And that means that we can union bound over the bad types. Okay, and this is what we wanted. I'll just mention one thing that we could, I'm even doing something wasteful here, right? Because I really don't need to remember the partition of each row. I just need to know the distribution of the partitions, because again, I don't care about permuting the rows. But it's not, because it already works here, it's not really important to me right now to try and do this additional optimization. It's easier, at least for the sake of this presentation, to just think of us as remembering exactly the order of the ordering of the partitions associated with the rows, and that also allows us to be able to talk about properties which are not even symmetric to coordinate shuffling if we want. I don't know if we do, but this is something we gain by doing that. Anyway, it's more convenient for this presentation. Okay, so I explained what are the types that we're going to use. And next, we're going to talk about, this is going to be after the break, we're going to talk about how, in the framework of these types, we can reason about this decodability of read-solvent codes. We can do that.
Thank you. Time for a couple of quick questions. Yeah. Not, I guess I'll take a break and continue at 11 o'clock.